All right, I'm trying to go through these notes fairly quickly for acids and bases. One, because then you don't have to watch this long a video, and two, because I have like 12 minutes until my next class comes in. So first of all, acids and bases, some just general properties. So acids and bases, a lot of times think of them as being opposites. People are really familiar with acids being reactive and dangerous. And bases, well, if acids are dangerous, then bases, if they're opposites, they must be, hey, they're okay and everything. But bases, they're also very reactive, but they react in a different way. So this just gives us some properties that we should look for in terms of acids. Now, touch and taste are not really good lab techniques for how to differentiate between the two of them. Obviously, their electrical conductivity, both are strong, so that's not a good way to differentiate. How they react to metals is a good way. And then really the best way to differentiate between acids and bases is like what we did in lab, and is to use an indicator, some chemical that turns. And there are lots of other reactions too that aren't on the table that acids do that bases don't, bases do that acids don't. But if you just want to test if something's an acid or base, you would use one of these indicators to take a look at it. So some really common ones is the phenolphthalein, knowing that that goes from pink to white here on the end, or pink to actually to colorless, I should say, not to white. Okay, is a really common one that we'll be using in lab. Litmus is probably one that you've used before. Bromothymol blue is very likely one that we could end up using in class. So those are probably the most common ones in terms of what I have to use in my classroom. Okay. So there's different ways to define, like on the chemical level, what makes an acid and what makes a base. And one of those is how do they behave in water. So acids are chemical. So if here's my acid molecule here, and if I take my acid molecule and I throw it into some water, okay, my molecule breaks up and it throws off an H, or a proton, a hydrogen atom. And that proton then, when it's in water, that's what does the business of an acid when an acid's in water. That's what makes all these reactions happening. It doesn't really matter what the rest of the junk is in the acid. It's mostly what the proton is. Okay, the rest of it does matter in some ways, and that it matters in terms of what, how likely that H is to come off in the first place. Bases that are defined, when you put a base in water, the OH comes off. Okay, and so the OH is what does all the work in water when something is a base. Okay, so when we're testing to see if something is acidic or basic, we're testing what is it, how much H and how much OH are in water. And as we'll see, there's always some of both of them, but where's the balance lie? Is most of it H and some of it OH, or is most OH and some of it H? And that tells us if it's acidic or basic. Okay. Another definition of, these are examples of arenous acids when they dissolve in water. And so I want you to know what this generic reaction looks like. That when I react an acid to water, I take HA as just my generic acid and make it to water. And what happens is the water then becomes H3O plus. Really, it's not ever just this naked H plus running around. And then the A minus. And so that just looks kind of like this, where just like an H just exchanges from one place to another. And really, a lot of acid-base reactions, that's all it is. It's just H is exchanging from one place to another. So I would write out this reaction specifically. So like HNO3, so the NO3 is my A, plus H2O goes to H3O plus NO3 minus. So that's just the generic reaction for what happens when you put an acid into water. Oops, wrong way. When you put a base into water, basically what happens is the base breaks up into its constituent ions. Okay, at least the arenous bases. So when I put this base into water, all that happens is, again, these OHs fall off. Okay, so that is an example of that. Okay, so again, I want you to know this general reaction. If I ask you a question like, what does it look like when calcium hydroxide reacts in water? You should be able to turn back to this generic reaction here, and you should be able to just plug in, like, well, M in that case is Ca for calcium. Okay, so this is really important to have right there. Neutralization reactions then is like we learned earlier about 5 different classifications of reactions. And neutralization reactions really can be thought of as double replacement reactions from earlier. But what happens when you react an Arrhenius acid with an Arrhenius base, you always make water, okay? And then you make some kind of salt. So to a chemist, salt is more of a broad term than to like your everyday person. When I say salt, everybody knows I mean the stuff that you put on your French fries. To a chemist, when you say salt, it just means like an ionic compound that can be made by reacting an Arrhenius acid and an Arrhenius base together. So if we look at what happens in this reaction, again, you can think of it as a double replacement reaction where we've got some partner switching happen. The H becomes partner with the OH. The Na gets partnered with the Cl. Okay, and so again, here's our water, here's our salt, and in this case, it's actual table salt. Okay, so again, that's what a neutralization reaction looks like. And so I might ask you questions. What would the neutralization reaction between potassium hydroxide and sulfuric acid looks like? And you should be able to show me how that makes water, and then the salt, which in that case would be potassium sulfate. Okay. So again, to look back over these, if you want to write an equation for HCl dissolving in water, you would go back to this reaction here, the HA plus H2O reaction, and you would use that as a model. So that I'm going to have HCl as my HA plus H2O, and I'm going to make H3O plus and Cl minus. If I want to write the reaction for aluminum hydroxide in water, again, I go back now to this one as my model because that's a base. So I've got Al, OH3, so the Al is like my M and the 3 is like my X, would become Al3 plus 3 OH minuses in water. And if I wanted to write the equation for the neutralization reaction of HCl and MgOH2, for this one I would go back and I would look at my generic neutralization reaction and realize, okay, well HCl is HA and MgOH2 is the MOHX. Okay, so HCl, because HCl has just one H and MgOH2 has 2 hydroxides, I need to have 2 HCl's to make this happen. So I have 1 H for every OH, and each H-OH pair makes a water, so I end up with 2 H2Os. And then the MgCl2, okay? Because Mg is 2 positive and Cl is 1 negative. So in talking about acids and bases, we talk about the pH scale a lot. So the way the pH scale works is right in the middle is considered neutral. The acid is the low side, so acid is when you are below 7. And bases are above 7. Okay? The thing about pH scale that I want you to know is pH is what's considered a logarithmic scale. Now, whenever you change by 1 pH unit, the concentrations of things change by a factor of 10. Okay? So, this is hard to read, probably not the best image I've blown up this big, but the pH of 5, okay, the amount of hydrogen ions, so the H plus concentration, is 10 to the negative 5th. Okay? The OH minus concentration is 10 to the negative 9th. If I go 1 pH unit over, okay, then let's get this out of the way. If I go 1 pH unit over, then my H plus goes to 10 to the negative 4th. So that's a factor of 10 difference. You get 10 times as much H plus. Okay, so H plus increases as you go this way. You get more H plus. Okay, as you get to the more acidic side, and OH minus increases as you go this way. The amount of H plus and OH minus are always related to each other. Okay, as one goes up, the other goes down, and they go up by the same amount. So if H plus goes up by 10 times, OH minus goes down by 10 times. And if you multiply the two together, it always equals, it always equals 10 to the negative 14. And that has to do with the equilibrium between water and water itself splitting up into H plus and OH minus. Okay? So again, the lower the pH, the more hydronium, and the hydronium is the H3O plus, and the less hydroxide, and that's the OH minus. And then the higher the pH, it flip-flops. As your pH goes higher, H3O plus goes down, OH minus goes up. Okay? The formula is then to go back and forth, because again, pH is a logarithmic scale. So I think this was on the other slide, but I'll put it here again, and we'll work some of these problems tomorrow in class. pH is equal to the negative log of whatever the H plus concentration is. Okay? And so the H plus concentration is equal to 10 to the minus pH power. Sometimes we're working with OH minus. So we can define a term called POH, which is equal to the negative log of OH minus concentration. So the OH minus concentration is equal to 10 to the POH power, to the negative POH power. OH minus and H plus are related to each other, and I already showed you that. pH plus POH always has to equal 14. So that's a nice, easy relationship to use. Okay? When talking about acids and bases, sometimes I talk about acids, this is a strong acid or this is a weak acid. And sometimes we can refer to acids like this is concentrated, this is dilute. And so I want to show you the difference between strong versus weak acids. A strong acid, when you put it in water, completely breaks up into H plus and A minus. So for a strong acid, I would find all of my acid in its ionized form, so it has the H pluses are free to go and attack things. Whereas with a weak acid, most of my acid molecules are together, and only some of them are broken up and free to do something. Okay? So that's the difference between strong and weak. Okay? The difference between concentrated and dilute, if something is concentrated, you have a lot of them. If something is dilute, you just have a few of them. Okay? So you can have a dilute strong acid that could still be as strong as a concentrated weak acid. Okay? So like HCl is a strong acid, vinegar is a weak acid, so I could have a dilute solution of hydrochloric acid that could still be stronger than a concentrated vinegar solution. Okay? All right, and that's actually all we're going to go through in these notes. Again, we'll work a few problems and examples together as a class to kind of really solidify this, but hopefully you'll have seen the terms and this will help you out get started.